go on chatting till about 9 o'clock, and then we'll make a break, and anything after that will be sort of informal discussion in small groups. Okay? This is a fairly straightforward question. What's the relationship between atomic structure and dark matter? I'll talk about dark matter next time. Something like, 80% of the stuff in the universe is something we have no idea what it is. So the answer is nobody knows. Feel free to just butt in during this time, okay? Sort of put your hand up if you want to say something. Do you as a scientist not find that a theory which depends on so many inexplicable numbers is a most unsatisfactory one? Would you be able to accept it if you were not a Christian? Well, it's unsatisfactory in the sense that there's no fundamental explanation. It's very satisfactory in the sense that it agrees with experiment. I mean, the fundamental rule in science, I think, is do the experiment, see what happens. And so a theory which does agree with the experiment is really a pretty good theory, but you'd like a proper explanation. At this sort of level, why has carbon got a mass of 12 and oxygen a mass of 16? Oh well, because carbon's got 6 protons and 6 neutrons, and oxygen's got 8 protons and 8 neutrons. So you're explaining something in terms of something simpler, right? We would like to have the standard model explained in terms of something simpler. So no question, it's not satisfactory in that sense. It's a sort of working model. You know, engineers, and this question came from an engineer, engineers, I think, are happy to use reliable data which works. And the standard model is reliable in that it works, but nobody thinks it's a really satisfactory theory. Did that, let me come back on that. What does it mean to say something exists but has no mass? I've simplified here. When particles move, well, basically mass, let me go back to elementary things. Mass is resistance to acceleration. If something's got lots of mass, it's hard to get moving, okay? You have to push it, and something which is light you can get going very fast, something which is heavy you have to push very hard. My brother was a consultant in nuclear medicine, and they had a massive room made of very thick steel in order to put people inside it, and you could be sure they weren't getting radioactivity from outside. And you had this door, and you sort of, oh, the door is stuck, and you started pushing it, and you couldn't stop it. What's the door going? It was a huge door that, you know. So mass is something that's hard to move and hard to stop. Now, when things get going fast, their mass increases. This is something that relativity says. So these protons that are going very, very close to the speed of light actually have very, very much bigger mass than when they started, okay? So when things are moving, they have more mass, and they can never get quite to the speed of light, because if they got to the speed of light, the theory says they'd have infinite mass. But particles that have no mass do go at the speed of light and do have energy, okay? So a photon has no, well, the technical term is rest mass. A photon never rests. It either is going at the speed of light or it's not there at all. But photons do have energy, so they do have mass. So particles which have no mass still exist. Well, they don't have a rest mass, but they're going at the speed of light and they do have energy, so they do have mass. Interestingly, I have misled you about the proton and the neutron, because I said the neutron and the proton have 3 quarks in them. And you may have thought, add up the masses of the quarks and you get the mass of the proton. If anyone did that, you'd have got a very bad answer. The masses of the quarks don't add up to anything like the mass of the proton. The quarks are quite light. Most of the mass of the proton is the gluons belting around inside at the speed of light. Okay? There's lots and lots of energy inside a quark due to the gluons, and that is most of the mass. So things can have mass even though they have no rest mass. Have I answered the question? Neutrinos were thought to be particles without mass that therefore went at the speed of light. We now know they've got a very little bit of mass and they go nearly at the speed of light.
in simplistic terms, we often talk about things that are spiritual, are kind of without mass or something, and things that are physical or tangible, material has mass, and that's probably just a terrible way to think, because it sounds like you're obviously describing things that are not material.
I think there are things that are real that don't have mass. For example, an idea. I think an idea is something real. It hasn't really got a mass. And again, spiritual things, I think, are real but don't have mass. A photon, I think, is real and does have mass, although it never stops, so it's got no rest mass. I'm going to move on. What is information, and which came first, matter or information? That's a very deep question. And I think I'd like to put that off till the third talk, because then we'll be talking about trying to make a really fundamental theory that explains things. So, I mean, in principle, I suppose it's possible to say that information causes theories which substantiate matter. Anyway, I think we're talking very highfalutin stuff. The standard model of particle physics is really very down to earth and practical, even though it's very mathematical. So I'm not sure I can answer that question. I want to come back on that, because I haven't really got the, and which came first, matter or information. We'll come back next time to the idea of the Big Bang and the beginning of everything and whatnot. So I'm going to sort of just duck that question. Here's a question here, which I think I'm going to rephrase the question and say, what's the chance of life existing? In other words, I've said in my talk, it seems to be a huge fluke, a huge coincidence that life is possible. Can you put a number on that? Is it 1 in 100, or 1 in 1,000, or 1 in a million? Or 1 in 100 million, or 1 in 10,000 million, or whatever. It's a serious question which is very difficult to answer for a number of reasons. One reason is that we do not know how the different parts of the theory vary with each other. So it's fairly easy to say, okay, the strong nuclear force couldn't be, shall we say, more than 10% weaker or 20% stronger. That's fairly straightforward. But the carbon resonance depends on the strong nuclear force and the electric force and the masses of the proton and the neutron. Now, do they all vary together? If you vary the strong nuclear force, does the mass of the proton vary automatically, or doesn't it? Do you see what I'm saying? That it's very hard to know how everything varies together, so it's extremely difficult to make a serious calculation, even on this elementary basis of saying, well, let's put this up by 10% and that one down by 20%. You could do a sort of a calculation and do something like that. But again, how much do you vary it? Are we allowed to vary by up and down by 10%, or up and down by a factor of 10, or up and down by a factor of 1,000,000? If you've got no fundamental theory which explains it, what's to put the limits on? I mean, if the strong force has got to be within what it is, let's say the mass of the neutron. Suppose that the mass of the down quark has got to be within 1% of what it actually is. Okay? Well, 1% of what? Is the down quark allowed to be 1,000,000 times heavier than it is? Is it allowed to be 1,000,000 times lighter than it is? In which case 1% is 1 part in 100 million. Or is it only allowed to be twice as big as it is? Do you see the problem? It's very difficult to do anything quantitative in this area. The other thing I would say, I have not got time to talk about any of the other aspects of fine-tuning. For example, water is absolutely crucial to life. The structure of DNA and proteins are absolutely crucial to life. How would they be affected if we had changed the mass of the electron a bit? Or if we changed the strength of the electric force a bit? How much could we vary the strength of the electric force before water wouldn't work? Or before DNA wouldn't work? I don't know. But there are all these sort of questions as well. I was talking about plate tectonics, which seems to be a bit of a fluke and very important for the history of life on Earth. How much could we change magnetism of iron before plate tectonics are going to work? You know? There's a whole series. I mean, my gut feeling is, golly, everything is incredibly finely balanced. But that's only a gut feeling, it's not a quantitative thing. That's the list of questions. Are there more questions?
I wonder whether you can use the argument that everything's so sensitive to support the case for a designer behind the universe, since we can't exist in a universe that doesn't have the right values for the constants.
Yeah.
So it's sort of, as it were, if you like, it's inevitable. In any universe where the constants are right to allow life to emerge,
yeah.
we'll look at it and go, gosh, what a fluke.
Can I rephrase that, because it won't be on the recording? I think what's being said is, it's not a fluke that we're here, because if the constants were such that life wouldn't be possible, we wouldn't be here to ask the question.
Yeah.
Okay? Now, I think there's force in that, and this is the sort of thing I'll be discussing in talk 3 at some length. But can I just give an example, which I think is a counter-example with some force. It's not mine, it's a philosopher called Leslie. A man is sentenced to death by firing squad. There are 50 people who fire guns at him. But he survives. But there's no point in him asking the question, why am I here? Because if I hadn't survived, I wouldn't be here to ask the question. Do you get the point? I think there is some value in that discussion. I think somebody who was fired at 50 times and survived would not naturally say, oh, well, of course, there's no point in me asking the question if I wasn't alive.
Oh dear.
If I wasn't alive, I wouldn't be asking the question. That's why we bought a Mac Pro instead of another.
He's under your foot.
Vitally. But that's a question which we'll look at. It's a very serious objection, and will be looked at in detail in talk 3.
Paul, question. Thinking about quantum entanglement, where particles which are a long way apart seem to know, and when one changes, the other changes.
Yeah.
Which of the forces